Hi friends, in this session we introduce the concept of permutations. A permutation on a set is a one-to-one function from the set onto itself. We exhibit that the set of all permutations on a finite set is a group under function composition. Two examples of symmetric groups and Cayley's theorem with statement and proof will be discussed. The conclusion of the session is with a discussion on regular representations. We begin with a review on functions between sets. Quick review of functions. Definition. A function phi from a set A into a set B is a rule that assigns to each element A of A exactly one element B of B. We said that phi maps A into B and that phi maps A into B. We denote phi maps A into B by phi of A is equal to B. The element B is the image of A under phi. The fact that phi maps A into B will be symbolically expressed as follows. Figure 1 helps us to visualize a function. For a function phi from A to B, the set A is the domain of phi. The set B is the codomain of phi, and the set phi of A is equal to set consisting of phi of A such that A belongs to A is the image of A under phi. If phi and psi are functions with phi from A to B and psi from B to C, then there is a natural function mapping A into C as illustrated in figure 2 that one can get from A to C via B using the functions phi and psi. This functions from A into C is the composite function consisting of phi followed by psi. We write psi of phi of A is equal to C. It is convenient to denote this composite function by psi phi. Note that the product psi phi for phi followed by psi has to be read from right to left. The notation psi composition phi is also used for this composite function. Definition. A function from a set A into B is one-to-one if each element of B has at most one element of A mapped into it. A one-to-one function is also called an injection. Definition. A function from a set into B is onto if each element of B has at least one element of A mapped into it. An onto map is also called surjection. Method of verifying whether a function is one-to-one or onto. 1. To show that phi is one-to-one, we show that phi of A1 is equal to phi of A2 implies A1 is equal to A2. This is equivalent to show that A1 not equal to A2 implies phi of A1 not equal to phi of A2. 2. To show that phi is on to B, we show that for each B in B, there exists A in A such that phi of A is equal to B. Definition. A function that is both one-to-one and onto is a bijection. If phi from A to B is one-to-one and onto, we denote it as follows. Example 1. Since f from R to R defined by fx equal to 2x plus 3 is both one-to-one and onto, it is a bijection. F from R to R defined by fx equal to x square is not one-to-one and hence it is not a bijection. F from R plus to R plus defined by fx equal to x square is a bijection. Permutation of a set. Definition. A permutation of a set A is a function that is both one-to-one and onto. Example 2. Let A is equal to set 1, 2. List all the permutation of the set A. Solution. It can be seen that the map sigma from A to A defined by sigma of 1 is equal to 1 and sigma of 2 is equal to 2 is both one-to-one and onto and hence is a permutation on A. Another permutation is psi defined by psi of 1 is equal to 2 and psi of 2 is equal to 1. There is no other permutation on A. Hence, the only permutations on A are sigma and psi defined above. Hence, the collection of all permutation of the set A is set sigma psi. The mappings sigma and psi can be denoted as in figure 3 and 4 respectively. We denote sigma and psi in a more standard notation as below. In sigma, we write in second row 1 below the 1 in the first row to indicate that sigma of 1 is equal to 1. Similarly, we write in the second row 2 below 2 in the first row. In psi, we write in the second row 2 below the 1 in the first row to indicate that psi of 1 is equal to 2 and so on. As sigma and psi are function, the compositions of sigma and psi can be discussed. The two composite functions are sigma psi and psi sigma. We compute them as follows. Sigma psi of 1 is equal to sigma of psi of 1, which is equal to sigma of 2 is equal to 2, and sigma psi of 2 is equal to sigma of psi of 2 is equal to sigma 1 is equal to 1. Psi sigma 1 is equal to psi of sigma of 1 is equal to psi of 1 is equal to 2, and psi sigma of 2 is equal to psi of sigma of 2 is equal to psi of 2 is equal to 1. They can be denoted as follows. Hence, the function composition is a binary operation on a set sigma psi of permutation on A is equal to set 1 2, denoting a permutation. As in the previous example, we write a permutation sigma on A is equal to set 1 2 etc. n in the following fashion. Permutation groups. We now show that function composition is a binary operation on the collection of all permutation of a set A. Let A be a set and let sigma and tau be permutations of A so that sigma and tau are both one-to-one functions mapping A onto A. The composite function sigma tau, defined schematically as follows, gives a mapping of A into A. Now, sigma tau on A must be read in right to left order. First apply tau and then sigma. Let us show that sigma tau is a permutation. That is to show that sigma tau is both one-to-one and onto. Sigma tau of A1 is equal to sigma tau of A2, which implies sigma of tau of A1 is equal to sigma of tau of A2, which implies tau of A1 is equal to tau of A2 since sigma is 1 to 1, which implies A1 is equal to A2 since tau is 1 to 1. Hence, sigma tau is 1 to 1. Let A belongs to A. Since sigma is on to A, there exists A dash in A such that sigma of A dash is equal to A. Since tau is on to, there exists A double dash such that tau of A double dash is equal to A dash. Thus, A is equal to sigma of A dash is equal to sigma of tau of A double dash, which is equal to sigma tau of A double dash. That is, corresponding to a given A in A, there exists A double dash in A such that A is equal to sigma tau of A double dash. Hence, sigma tau is onto A. That is, sigma tau is both one-to-one and onto, and hence is a permutation on the set A. We have shown that for any given permutation sigma tau on a set A, the composition sigma tau is again a permutation on the set A, showing that function composition is a binary operation on the collection of all permutations of a given set. Definition. The function composition on the collection of all permutation of a set A is a binary operation, and this binary operation is called the permutation multiplication. Example 3. Suppose that A is equal to set 1, 2, 3, 4, 5 and that sigma and tau are two permutation on the set A defined by sigma is equal to 1 to 4, 2 to 2, 3 to 5, 4 to 3, 5 to 1 and tau is equal to 1 to 3, 2 to 5, 3 to 4, 4 to 2, 5 to 1. Find sigma tau. If I is equal to 1 to 1, 2 to 2, 3 to 3, 4 to 4, 5 to 5 is another permutation, verify that I sigma is equal to sigma I and I tau is equal to tau I. Solution. Sigma tau of 1 is equal to sigma of tau of 1 is equal to sigma of 3 is equal to 5. Sigma tau of 2 is equal to sigma of tau of 2 is equal to sigma of 5 is equal to 1. Sigma tau of 3 is equal to sigma of tau of 3 is equal to sigma of 4 is equal to 3. Sigma tau of 4 is equal to sigma of tau of 4 is equal to sigma of 2 which is equal to 2. Sigma tau of 5 is equal to sigma of tau of 5 is equal to sigma of 1 is equal to 4. In the standard notation, we have sigma tau is equal to permutation 1 to 5, 2 to 1, 3 to 3, 4 to 2, 5 to 4. It can be seen that I is the identity mapping and also I sigma of 1 is equal to I of 4 is equal to 4. I sigma of 2 is equal to I of 2 is equal to 2, etc. Hence, I sigma is equal to permutation 1 to 4, 2 to 2, 3 to 5, 4 to 3, 5 to 1 which is equal to sigma. Also, sigma I of 1 is equal to sigma of 1 is equal to 4. Sigma I of 2 is equal to sigma of 2 is equal to 2. Hence, sigma I is equal to sigma. Similarly, it can be seen that I tau is equal to tau I. Theorem 1. Let A be a non-empty set and let SA be the collection of all permutations of A. Then SA is a group under permutation multiplication. Proof. The discussion just before the definition of permutation multiplication shows that permutation multiplication is a binary operation on SA. G1. Permutation multiplication is associative. We have to show that sigma tau of mu is equal to sigma of tau mu. For sigma, tau, mu belong to SA. For this, we have to show that sigma tau of mu of A is equal to sigma of tau mu of A for each A in A. Now, sigma tau of mu of A is equal to sigma tau of mu of A is equal to sigma of tau mu of A is equal to sigma of tau mu of A. Hence, the associative property is satisfied. G2. Existence of identity. The permutation I such that IA is equal to A for A in A obviously act as identity because I composition sigma is equal to sigma which is equal to sigma composition I for sigma belong to SA. I is called the identity permutation on A. Hence, G2 is satisfied. G3. Existence of inverse. For a permutation sigma, define sigma inverse to be the permutation that reverses the direction of the mapping sigma. That is, sigma inverse of A is to be the element A dash of A such that A is equal to sigma of A dash. The existence of exactly one such element A dash is a consequence of the fact that as a function sigma is both 1 to 1 and onto. It is clear that sigma inverse of A is equal to sigma of A dash which is equal to A, and sigma inverse of sigma of A dash is equal to sigma inverse of A which is equal to A dash. So that sigma inverse sigma and sigma inverse are both the identity permutation I. Thus, G3 is satisfied. This completes the proof of the theorem. Definition. If A is the finite set 1, 2, etc. n, then the group of all permutations of A is the symmetric group of n letters and is denoted by Sn. Note that Sn has n factorial elements, where n factorial is equal to n into n minus 1 into n minus 2 into etc. 3 into 2 into 1. Example 4. For 2 permutation, A is equal to permutation 1 to 2, 2 to 3, 3 to 1 and B is equal to permutation 1 to 3, 2 to 1, 3 to 2. Show that AB is equal to BA is equal to I, the identity permutation on the set A is equal to 1, 2, 3. Solution. AB is equal to permutation 1 to 2, 2 to 3, 3 to 1 into permutation 1 to 3, 2 to 1, 3 to 2 which is equal to permutation 1 to 1, 2 to 2, 3 to 3 which is equal to I. BA is equal to permutation 1 to 3, 2 to 1, 3 to 2 into permutation 1 to 2, 2 to 3, 3 to 1, which is equal to permutation 1 to 1, 2 to 2, 3 to 3, which is equal to I. Hence, AB is equal to BA is equal to I. Example 5. Suppose that A is equal to set 1, 2, 3, 4, 5 and sigma is equal to permutation 1 to 4, 2 to 2, 3 to 5, 4 to 3, 5 to 1. Find the inverse permutation sigma inverse. Solution. Since sigma is both 1 to 1 and onto, its inverse map exists and we denote it by sigma inverse. Clearly, sigma inverse is 1 to 1 and onto and hence is a permutation on A. Now, we find sigma inverse. Sigma permutation from 1 to 4, 2 to 2, 3 to 5, 4 to 3, 5 to 1. Hence, in sigma inverse, permutation 1 to 5, 2 to 2, 3 to 4, 4 to 1, 5 to 3 and we denote it in the standard form sigma inverse equal to permutation 1 to 5, 2 to 2, 3 to 4, 4 to 1, 5 to 3. It can also be seen that sigma inverse is equal to permutation 1 to 4, 2 to 2, 3 to 5, 4 to 3, 5 to 1 into permutation 1 to 5, 2 to 2, 3 to 4, 4 to 1, 5 to 3, which is equal to permutation 1 to 1, 2 to 2, 3 to 3, 4 to 4, 5 to 5, which is equal to I. Similarly, sigma inverse of sigma is equal to I. Example 6. Find the inverse of the permutation 1 to 5, 2 to 3, 3 to 4, 4 to 6, 5 to 1, 6 to 2. Solution. The inverse of the given permutation is permutation 5 to 1, 3 to 2, 4 to 3, 6 to 4, 1 to 5, 2 to 6, which is equal to permutation 1 to 5, 2 to 6, 3 to 2, 4 to 3, 5 to 1, 6 to 4. Example 7. For the permutation group S4, find the number of elements in the set consisting of sigma belongs to S4 such that sigma of 3 is equal to 3. Solution. If we fix sigma 3 is equal to 3 for sigma belong to S4, then sigma may have the action of any of the 6 possible permutation of the set 1, 2, 4. So, there are 6 possibilities for sigma. Hence, the number of elements in the set consisting of sigma belongs to S4 such that sigma of 3 is equal to 3 is 6. Examples of symmetric groups. Example 8. Symmetric group of 3 letters. Let A is equal to set 1, 2, 3. Then S3, the symmetric group of 3 letters has 3 factorial is equal to 6 elements and they are rho naught is equal to permutation 1 to 1, 2 to 2, 3 to 3. Mu 1 is equal to 1 to 1, 2 to 3, 3 to 2. Rho 1 is equal to permutation 1 to 2, 2 to 3, 3 to 1. Mu 2 is equal to permutation 1 to 3, 2 to 2, 3 to 1. Rho 2 is equal to permutation 1 to 3, 2 to 1, 3 to 2. Mu 3 is equal to permutation 1 to 2, 2 to 1, 3 to 3. It can be seen that rho naught mu 1 is equal to permutation 1 to 1, 2 to 2, 3 to 3 into 1 to 1, 2 to 3, 3 to 2, which is equal to 1 to 1, 2 to 3, 3 to 2, which is equal to mu 1, etc. Rho 1 mu 1 is equal to 1 to 2, 2 to 3, 3 to 1 into permutation 1 to 1, 2 to 3, 3 to 2, which is equal to permutation 1 to 2, 2 to 1, 3 to 3, which is equal to mu 3, etc. And one can complete the finite group table 1 as follows. From the group table, it can be seen that the symmetric group of 3 letters is not abelian. Hence, the symmetric group S3 is not cyclic. Also referring the group table, it can be seen that every proper subgroup of the non-abelian group S3 are abelian. Therefore, this gives an example that every proper subgroup of a non-abelian group may be abelian. Remark. There is a natural correspondence between the elements of S3 and the ways in which two copies of an equilateral triangle with vertices 1, 2 and 3, figure 5, can be placed, one covering the other. For this reason, S3 is also the group D3 of symmetries of an equilateral triangle. We use rho I for rotations and mu I for mirror images in bisectors of angles. The notation D3 stands for the third dihedral group. The nth dihedral group Dn is the group of symmetries of the regular n-gun. Order of the group Dn is 2n. Example 9. Let us form the dihedral group D4 of permutations corresponding to the ways that two copies of a square with vertices 1, 2, 3 and 4 can be placed, one covering the other, figure 6. D4 will then be the group of symmetries of the square. It is also called the octic group. We use rho I for rotations, mu I for mirror images in perpendicular bisectors of sides and delta I for diagonal flips. There are 8 permutations involved here and they are: rho naught is equal to permutation 1 to 1, 2 to 2, 3 to 3, 4 to 4. Mu 1 is equal to 1 to 2, 2 to 1, 3 to 4, 4 to 3. Rho 1 is equal to 1 to 2, 2 to 3, 3 to 4, 4 to 1. Mu 2 is equal to 1 to 4, 2 to 3, 3 to 2, 4 to 1. Rho 2 is equal to 1 to 3, 2 to 4, 3 to 1, 4 to 2. Delta 1 is equal to 1 to 3, 2 to 2, 3 to 1, 4 to 4. Rho 3 is equal to permutation 1 to 4, 2 to 1, 3 to 2, 4 to 3. Delta 2 is equal to permutation 1 to 1, 2 to 4, 3 to 3, 4 to 2. The group table 2 for D4 is given below. Note that D4 is non-abelian. Attention! Never confuse S4 with D4. S4 is a symmetric group of 4 letters with 4 factorial is equal to 24 elements, while D4 is a group with just 2 into 4 which is equal to 8 elements. Definition: a non-empty set equipped with a binary operation star is an algebraic structure. Let S star and S dash star dash be binary algebraic structures. An isomorphism of S with S dash is a one-to-one function phi mapping S onto S dash such that phi of x star y is equal to phi of x star dash phi of y for all x y belongs to S, equation number 1. If such a map phi exists, then S and S dash are isomorphic binary structures, which we denote as follows. Property 1 is called homomorphism property. Remark: in equation phi of x star y is equal to phi of x star dash phi of y considered above. The product x star y on the left hand side takes place in S, while the product phi of x star dash phi of y on the right hand side takes place in S dash. Usually we denote x star y by xy and phi of x star dash phi of y by phi of x into phi of y. Lemma: let G and G dash be groups and let phi from G to G dash be a one-to-one function such that phi of xy is equal to phi of x into phi of y for all xy belongs to G. Then phi of G is a subgroup of G dash and phi provides an isomorphism of G with phi of G. Proof: we show that the conditions for a subgroup are satisfied by phi of G. Closure property: let x dash y dash belongs to phi of G. Then there exists xy belongs to G such that phi of x is equal to x dash and phi of y is equal to y dash. By hypothesis, phi of xy is equal to phi of x into phi of y which is equal to x dash y dash, showing that x dash y dash belongs to phi of G. We have shown that phi of G is closed under the operation of G dash. Existence of identity element in phi of G. Let E dash be the identity of G dash. Then E dash phi of E is equal to phi of E is equal to phi of E which is equal to phi of E into phi of E. Cancellation in the group G dash shows that E dash is equal to phi of E. So, E dash belongs to phi of G. Existence of inverse element for each element in phi of G. For x dash belongs to phi of G, where x dash is equal to phi of x, we have E dash is equal to phi of E is equal to phi of x inverse is equal to phi of x into phi of x inverse, which is equal to x dash phi of x inverse, which shows that x dash inverse is equal to phi of x inverse belongs to phi of G. Hence, phi of G is a subgroup of G dash. That phi provides an isomorphism of G with phi of G now follows at once because phi provides a one-to-one map of G onto phi of G such that phi of xy is equal to phi of x into phi of y for all xy belongs to G. Cayley's theorem. Theorem 2. Every group is isomorphic to a group of permutations. Proof. Let G be a group. We denote the group of all permutations on the group G by Sg. We show that G is isomorphic to a subgroup of Sg. By the previous lemma, we need only to define a one-to-one function phi from G to Sg such that phi of xy is equal to phi of x into phi of y for all xy belongs to G. For let x belongs to G. Lambda x from G to G be defined by lambda x of G is equal to xg for all G belongs to G. We think of lambda x as performing left multiplication by x. The equation lambda x of x inverse C is equal to x into x inverse C, which is equal to C for all C belongs to G, shows that lambda x maps G onto G. If lambda x of A is equal to lambda x of B, then xa is equal to xb. So, A is equal to B by cancellation in the group. Hence, lambda x is 1 to 1. Being 1 to 1 and onto, lambda x is a permutation of G. We now define phi from G to Sg by defining phi of x is equal to lambda x for all x belongs to G. To show that phi is 1 to 1, suppose that phi of x is equal to phi of y. Then lambda x is equal to lambda y as functions mapping G into G. In particular, lambda x of E is equal to lambda y of E. So, x is equal to ye and x is equal to y. Thus, phi is 1 to 1. It remains only to show that phi of xy is equal to phi of x into phi of y. That is, that lambda xy is equal to lambda x into lambda y. Now, for any G in G, we have lambda xy of G is equal to xy of G. Also, lambda x, lambda y of G is equal to lambda x of lambda y of G, which is equal to lambda x of yg, which is equal to x into yg. Thus, by associativity, lambda xy is equal to lambda x into lambda y. Hence, phi of xy is equal to phi of x into phi of y. That is, we have shown that phi from G to Sg is a one-to-one function such that phi of xy is equal to phi of x into phi of y. Hence, by the previous lemma, phi provides an isomorphism of G with phi of G. Noting that phi of G is a subgroup of Sg. The theorem is proved. Remark. For the proof of the theorem, we could have considered equally well the permutation rho x of G defined by rho x of G is equal to Gx for G in G. We can think of rho x as performing right multiplication by x. It can be proved that these permutations form a subgroup of Sg, again isomorphic to G, but provided by a map mu from G to Sg defined by mu of x is equal to rho x inverse. Regular representations. Definition. The map phi in the proof of Cayley's theorem is the left regular representation of G, and the map mu in the preceding remark is the right regular representation of G. Example 10. Let us compute the left regular representation of the group given by the group table 3. By compute, we mean give the elements for the left regular representation and the group table. Here the elements are lambda E is equal to permutation E to E, A to A, B to B. Lambda A is equal to permutation E to A to B, B to E, and lambda B is equal to permutation E to B, A to E, B to A. The table for this representation is just like the original table with x renamed lambda x as seen in table 4. For example, lambda B is equal to permutation E to A to B, B to E into permutation E to B, A to E, B to A, which is equal to permutation E to E, A to A, B to B, which is equal to lambda E. For a finite group given by the group table, rho A is the permutation of the elements corresponding to their order in the column under A at the very top, and lambda A is the permutation corresponding to the order of the elements in the row opposite A at the extreme left. The notations rho A and lambda A were chosen to suggest right and left multiplication by A respectively. In this session, we have discussed the concept of permutation, citing some examples. We have proved that the set of all permutation on a finite set is a group under function composition. The statement and proof of Cayley's theorem and a brief discussion on regular representations have been made. Now, try to answer the following questions. Verify that the function f from R to R, where f of x is equal to 2x plus 3 is 1 to 1 and onto. Verify that the function f from R to R, where fx is equal to x square is not 1 to 1. Verify that the function f from R to R, where fx is equal to x square is not onto. Let sigma is equal to permutation 1 to 3, 2 to 1, 3 to 4, 4 to 5, 5 to 6, 6 to 2. Tau is equal to permutation 1 to 2, 2 to 4, 3 to 1, 4 to 3, 5 to 6, 6 to 5, and mu is equal to permutation 1 to 5, 2 to 2, 3 to 4, 4 to 3, 5 to 1, 6 to 6. Compute the following products in the permutation group S6. Tau square sigma, mu sigma square, sigma raised to minus 2 tau, sigma inverse tau sigma. Hope you enjoyed this session. See you next time. Till then, take care.